Hello and welcome. Very soon we'll be starting to this live presentation of how we do the electronic configuration when it comes to understanding the quantum theory and the atomic structures. So you do well to invite as many as possible that would tie in to this beneficial education video and share this video. You can like it if it will be beneficial to you. If there will be any question, you do well to also just write. So without wasting much of our time, let me now present myself. I'm Cleopas Zulu, tutor. So in this live presentation, we are going to look at how we do electronic configurations when it comes to advanced chemistry. So when it comes to O-level chemistry or lower chemistry, the electronic configuration that we do is very different when we are doing it with A-levels and advanced chemistry. And this is what we are going to look at here today. So I've presented this presentation here, and this guides us when it comes to the electronic configuration. When you want to write the electronic configuration of any atom that is on the periodic table, by simply remembering this, you are able to come up with the electronic configuration in a correct way. Now, when you look at this, you can see that we have 1s, 2s, 2p, and so on and so on. So these, the s, the p, the d, and the d, and the f represents the orbitals in which electrons can fall in. Now, when it comes to writing the electronic configuration, the first thing you would want to do is to know what is the maximum number of electrons that can be occupied in each and every orbital. Now, when it comes to the s orbitals, you can only have 2 electrons as the maximum number of electrons that can be occupied by the s orbital. So all these s, s1, 2s, 3s, 4s, 5s, 6s, 7s, can occupy a maximum number of 2 electrons. So you need to remember this point as we'll be proceeding in our lecture this evening. Then the p orbital can occupy a maximum number of 6 electrons. So 6 electrons is the maximum number of electrons that can be occupied by the p orbitals. Then when it comes to the d orbital, the d orbital electrons. So 10 electrons are the maximum number of electrons that can be occupied by the d orbital. Then last but not the least, we have the f orbital that can occupy a maximum number of 14 electrons. So when it comes to writing the electronic configuration, you need to remember the maximum numbers of electrons that each and every orbital can occupy. Because if you forget the maximum numbers, then it will affect how you will be presenting the electronic configuration. Now, this maximum numbers of orbitals is as a result, or rather maximum number of electrons is as a result of the number of orbitals they have. So the s has only one space, Then when it comes to the P, it has 3 spaces. When it comes to the D, it has 5 spaces. When it comes to the F, it has 7 spaces. So each space can occupy 2. So 1 times 2 gives us 2 electrons. 3 times 2 gives us 6. 5 times 2 gives us 10. 7 times 2 gives us 14. So when you just remember, S is 1, P has 3 rooms, D has 5 rooms, then F has 7 rooms. And then you multiply these by 2, it gives you the maximum number of electrons that each and every orbital can have. Now, after you know the numbers of electrons that can be occupied by each and every orbital, we are ready now to give some examples of elements, and we come up with the electronic configuration together. So let's start with the first element that we can look at on the periodic table. If you are following this video, you do well to get your periodic table, because most of the work we'll be doing here are based on the periodic table. So the first element we would like to see and learn how to write the electronic configuration is this one, sodium. Now, sodium is an element on the periodic table, and me, I have my periodic table there, and it tells me that sodium has the atomic number of 11. So this element has the atomic number, which is 11. So this is basically the number of electrons or the number of protons that are available when it comes to sodium. So let's write the electronic configuration of sodium using this model that we have here. Now this model tells us that the first electron should occupy the 1s orbit level there. Then it comes to, after this arrow ends, we go to the next here. So the next we have 2s. 2s ends, we come to 2p, then we go to 3s. After 3s, we go to 3p, then 4s. So just like that, you follow the arrows as they are moving. So let's start with the first one, that is sodium, and see how we can write the electronic configuration. So sodium has 11 electrons, so I'll put the 11 here. Then the 1s, remember the s orbital can occupy a maximum number of 2 electrons. So because 11 is more than 2, then the 1s level should be filled to its full capacity. So 11, if I less 2, I'm getting 9. So we still have 9 electrons that are available for us to be put or to use when writing the electronic configuration of sodium. So we go to the next one. After 1s, we are going to 2s. So 2s, the s orbital can occupy the maximum number of 2 electrons. So we are saying we are reducing this by 2, then we are putting the 2 there. So we are getting, that is, we are remaining with 7 electrons. Now from 2s, the next is 2p. So we have 2p there. 2p, the p orbital can have a maximum number of 6. We still have 7 electrons. So the p orbital, all the electrons can be used up there. So we are saying we are raising it by 6 and remaining with 1 electron. So this 1 electron now should go to the next orbital, which is the 3s. So we have 3s, which will now have the one that we have there. So by doing this, then we have managed to write the electronic configuration of sodium and this is the representation of the electronic configuration of sodium. Now, after you have this representation of this element, the other thing they can ask you is to show a compressed electronic configuration of this element. Now, how do you write the compressed electronic configuration? The compressed electronic configuration takes advantage of the noble gas. Now, on the periodic table, noble gases are in group 8 or group 18, depending on how you interpret the periodic table. So, noble gases are in the last group, which is group 8 there. Now, when it comes to the compressed electronic configuration, you look at the noble gas that is in the period before the element you have been asked. In this case, sodium is in period 3. The first period is where we find hydrogen. The next period is where there is a lithium. Then sodium is in period 3. So, if sodium is in period 3, what is the noble gas which is in period 2? So, the noble gas in period 2 is neon. So, we will put neon there as we are writing the compressed electronic configuration. Now, when we write this compressed electronic configuration, you look at the electrons that this noble gas has. Neon has 10 electrons. So 10 electrons are as a result of 2 plus 2 plus 6. So this is the electronic configuration of neon. Now, if this is the electronic configuration of neon, then it simply means the next one which we are remaining with is 3s1. Now, this is telling us that the sodium that we are writing is in period 3 and only 1 electron remained, and this is the compressed electronic configuration of sodium. So let's see if you are following. If there is any question, you can put that question in the comment section. Then you can also put the liking of this video if you have really followed the video, and if you have any question, do not hesitate to put that question in the comment section. Now, if this is the case when it comes to sodium, there are some information that we can get from the electron configuration when it comes to an element that we have. Now, when you look at the last level, in this case we are looking at this level, it has 3s1. There is a lot of information that we can get from this number. The first one is the period in which this element is. So the number, which is the principal quantum number, which is 3, gives us the period in which this element is. So sodium is in period 3. Then this number, which is the number of electrons in the outermost shell, gives us the group. So sodium then should be in a group 1. So you can get the number of electrons and interpreting them in the group, and also the principal quantum number to tell you the period in which the electron is. So we have seen how we can write the compressed electronic configuration of sodium, also the normal electronic configuration, and the information we can get from this. Now, what of if you have been asked to write the electronic configuration of sodium ion? what are you going to do? So for sodium ion, you are saying the last level tells you the number of electrons this element can lose. In this case, it can lose 1 electron. So it will make sodium ion, which will have positive 1 there. Then the electronic configuration will be 1s2, then 2s2, and 2p6. So this is the electronic configuration of sodium ion. So remember, ions are as a result of an element wanting itself to be stable. So these atoms want to be stable, and if there is a metal, or if it is a metal, it will lose the electrons so that it becomes stable. And when they are stable, they form the electronic configuration of a noble gas. Remember, noble gases are in group 8 of the periodic table. So this is how we can form the electronic configuration of sodium, and we have learned certain details on sodium there. Let's look at another example. We'll do 3 examples in our live session today. So the next example we can try is aluminium. Let's look at aluminium. Then after aluminium, we'll do iron. So aluminium, when you have the periodic table, you will notice that the relative atomic mass of aluminium is 27, but for writing the electronic configuration, we use the atomic mass, or the atomic number rather. So the atomic number of aluminium is 13. That is the atomic number of aluminium. So let's write the normal electronic configuration of aluminium, and you do well to try to write the normal electronic configuration of aluminium at your own time, and see if what we will have is same as what you made there. If it is the same, you simply like this video, you comment that you managed, then we will give you a feedback on how correct you did your work. So let's come back to aluminium there. Now, remember, the first level we should start with is 1s. So 1s will be the first one. So 1s, remember we have 13 electrons, so the s orbital can have a maximum number of 2 electrons. So we'll reduce this by 2 and we'll get 11. Then from there we'll go to the next level, which is the 2s. So from 1s we are coming to 2s. 2s, the s, we are remaining with 9 there. We'll go to the next one, which is after this we are coming to 2p. So 2p, the p orbital can have a maximum number of 6 electrons. So we will put 6 there. So after you remove 6 from 9, you are remaining with 3. So we'll put 6 there. And then you go to the next one. From 2p, the next one is 3s. So 3s. Then we know that the s orbital can have a maximum number of 2 electrons. So we'll say 2, we're remaining with 1. So you put your 2 there, then you go to the next. From this one, the next is 3p. 3p. So this becomes the electronic configuration of aluminium. So we have used up all the electrons that are variable, and this is the electronic configuration of aluminium. Now, what is the compressed electronic configuration of aluminium? So remember the compressed one, we said you look at the noble gas that is in the period before the period of the element in question. So aluminium in this case is in period 3. So what is the noble gas in period 2? The noble gas in period 2 is neon. So you put neon there. Then after you put neon, you say which period is this element. This element is in period 3. So you start from 3s to write this compressed electronic configuration. So we'll start from 3s. Neon has helped us to get rid of 10 electrons. So out of 13, we're only remaining with 3. So 3, 2 will be put in the s orbital, then 1 will be put in the p orbital. So this has helped us to write the compressed electronic configuration of aluminium. Now, we can ask further, what is the period and the group of this element? The information that you have on period and the group in which the element is. In this case, you look at the highest level. So if the highest level is having the same number, in this case, we have 3s and 3p. These are where you are finding the last electrons. So the period is 3. Then these 2 and 1 gives you the group. So the group is 2 plus 1, which is group 3. So it is simply telling you that aluminium is in period 3, group 3. So we have used the highest level, that is 3, that's the principal quantum number, and the electrons in the highest levels, which is 2 and 1, to get the period there. So this is how we get the period. Let's write ion of aluminium. What would be the ion of aluminium? So aluminium, because it is in group 3, it simply means for it will lose 3 electrons there. Now, if it loses 3 electrons, it simply means it will have 1s2, 2s2, then 2p6, and this becomes the electronic configuration of aluminium ion. So you have seen, you are able to come up with the electronic configuration of the normal representation, the electronic configuration using the compressed representation, and the electronic configuration of the ion of aluminium. Without wasting much of our time, if you have any question, we are simply saying you can still ask us that question. You can also follow us on Facebook and on YouTube if you want to learn more. So let's now look at the last example that we are doing today, which is in line with ion. So ion, we'll learn how to write the electronic configuration of it. And then we'll also look at 2 ions that are formed by ion, knowing that ion is a transition metal. So because it's a transition metal, it is able to change its formation of ions. So let's look at ion and remember the atomic number. The atomic number of ion is, when we go to the periodic table, the atomic number of ion is 26. So the atomic number of ion is 26. Now, when it comes to this atomic number of 26, we can write the electronic configuration of this element. So let's write the electronic configuration. So we have 26 electrons. So the first level we'll use is 1s. 1s. We are saying the s orbital can only occupy 2 maximum electrons. So 26 minus 2, we are getting 24 there. So we put your 2 there. And then we go to the next one, which is 2s. 2s, we are saying we have s which can only have 2 electrons. So we are putting 2. 24 minus 2 is giving us 22. And then we go to the next one. From 2s, we are going to 2p. The p orbital can have a maximum number of 6 electrons. So we are saying minus 6. So this minus 6, it will give us a number of 16. So 16 is the remaining electron that we have. Then you put 6 there. Then you go to the next. From the 2p, we are going to 3s. So 3s there. S orbital can only have 2 electrons. So we are putting 2 there. From in 16, if you remove 2, you have 14. After 3s, the next one is 3p. So we have 3p. The p orbital has the maximum number of electrons, that is 6. So in 14, we are reducing 14 with 6. So if you remove that, you remain with 8 electrons. So 8 electrons are the remaining electrons that we have. So if those are the remaining electrons, the 6 will be put here. Then you say comma. Then from 3p, the next is 4s. 4s. So s can only have 2 electrons. So minus 2, we are remaining with 6, so we'll put our 2 there. From 4s, we are going to 3d. So 3d, we will now get all 6 electrons, because the maximum number of electrons for d orbital is 10, and 6 is less than 10. So all the 6 electrons will go in the 3d there. So this is how we write the electronic configuration of ion. Now, after you know the electronic configuration of ion, we can write its compressed configuration of ion. As we have already said, we look at the period on the periodic table. So you look at the period in which ion is. So the first period is where hydrogen is. The next period is where lithium is. The third period is where sodium is. That is where ion is. Now we say the noble gas that is before that period, that's the noble gas we use. So the noble gas which is in period 3, in this case, it is argon. So we use AR. That is the noble gas that we'll use when we are coming up with the compressed electronic configuration. Noble gas. You go to the next level, which is, we are now in period 4. That's where ion is. And if ion is in period 4, then we are saying we will start with 4s, then we'll put 2 there. Then from 4s, what is the next? The next is 3d. So the next will be 3d6. So this is the electronic configuration of configuration. So we have seen that this is normal electronic configuration. This is the compressed electronic configuration. For the transition metals, we'll do a very good video on how you determine the period, because sometimes, or rather the groups, because sometimes the periodic table is subdivided on the transition metals. But the highest level of the principal quantum number can tell you that aluminium, rather ion, is in the 4th period. Let's see, how do you write the electronic configuration of aluminium 2+? Because this is the first ion that can be formed from rather ion. How do you write ion 2? It is a rhyme, ion of ion. Anyway, so let's see how you can write this one. Now this one is simply telling you that 2 electrons have been given out by this atom. So which are the 2 electrons that will be given out? The 2 electrons that will be given out are in the highest orbital there, that is the 4s2. So we'll remain with 1s2, then 2s2, 2p6, 3s2, 3p6, and 3d6. So this is the electronic configuration of, now what will be the electronic configuration of ion 2 in terms of compressed? The compressed electronic configuration, we are simply saying it's only these 2 electrons that have been lost. So you can say it is argon and 3d6. So this is the electronic configuration of ion in terms of a compressed electronic configuration. So this is how we write the electronic configuration of ion 2. Let's look at ion 3. So I'll remove ion 2 there and show how we write the electronic configuration of ion 3. Ion 3. Now ion 3 is simply telling us that 3 electrons have been lost by this element, it being a metal. So where are these 3 electrons going to come from? 2 of them will be from the 4s, the 1 will be from D. So we'll say it will be 1s2, 2s2, 2p6, 3s2, 3p6, and this one will go, then the 3d will be reduced by 5. So that the total number of electrons compared to the atom and the ion has a difference of 3. So this is the electronic configuration of ion 3 ion there. In terms of the compressed one, we can say ion 3, when it comes to the compressed one, it has argon there. Then the next one will be this, which is 3d5. So this is the compressed electronic configuration of ion 3. Now, what you have noticed here is when it comes to transition metals, we are able to have different electronic configurations depending on the number of electrons that have been lost by such a metal. So what have we seen in this presentation or in this video today? The first thing is you need to know the maximum number of electrons that can be occupied by each orbital. The s orbital can occupy a maximum number of 2 electrons. The p orbital can occupy the maximum number of 6 electrons. The d orbital can occupy the maximum number of 10 orbitals. Then the f can occupy the maximum number of 14 electrons. After you know that, we are saying you need to remember this and how the arrows are used when it comes to writing the electronic configuration. So once the arrow ends, you go to the next one. Once it ends, you go to the next one, just like that, as you continue writing the electronic configuration. We have also seen that if the element is not in the transition, determine the group and the period that element is. So hope you have followed this video, and if you have any question, just put that question in the commentary section and the team will give you a feedback. Until next time, thank you so much for watching. This is Zuluba Consultants. It is. Bye-bye.